There we go. Good. Okay. We were talking about valuation domains last time. So let me give you this theorem, and then I'm going to do some examples. And I'm not going to prove this because I want you all to go through some of the details later. Let K valuation V. Right. The set of elements K in X in K such that the valuation of X is greater than or equal to 0, union 0 is the valuation domain to V. Y'all might have sort of picked up on this last time, because in the last time I constructed a bunch of valuations on the field by first constructing the valuation domain. I said, hey, look at this example that we had before. This was a valuation domain. And then I took the quotient field and said, oh, look, there's my valuation. You can work in reverse. Let K be a field with valuation V. The set of all elements X and K such that the valuation is greater than or equal to 0. And here I mean by 0, I mean this is the 0 of our totally ordered abelian group. So this is, of course, this is a generalization of, familiar totally ordered abelian groups like the integers or the real numbers. But in any abelian group, you have a 0 element, right? And everything that is greater than or equal to 0 are the non-negative elements of the group. So if you take everything in K such that the valuation takes you to the non-negative elements, then this is a valuation domain associated to V. And of course, you better throw in 0 as well. Let me point out that K also, any field is a valuation. And for example, you can take a valuation on the field just to be everything goes to 0, except for 0, I guess. And in that case, the valuation domain for that valuation, the trivial valuation, will be the field itself. Let me give you another example. I'm curious. How many of you have encountered the p-adics in your travels, the p-adic integers? Some of you maybe? P-adic integers? All right. Well, we'll talk about that a little bit. But before we do, let me give a plug for the math club today. It's going to be the first time I've been in the math club for a couple of weeks, and it's going to be a good one. Ben Breen, it'd be great to turn out and see his talk because he's a visitor this year, and he's really kind of a visitor in ADM, but he's going to talk about redistricting, which is a hot topic. And it's going to get hotter. So I would encourage you to be there at 5 for that. So here's a good example. Valuation domain. CP. I'm going to use this example to tell you about the p-adics, and then I'm going to tell you in another way. Now, this is, I hope, kind of a familiar example now. This is the set of all fractions and rational numbers where the denominator is relatively prime to p. We've seen that this is valuation domain. In fact, it's a PID with only one prime, and P, ZP, is unique maximal ideal. Now, all of us here grew up on calculus, right? And we grew up on measuring stuff on the real line, right? The distance between 1 and 2 on the real line is 1. You just subtract the difference. However, there are other ways to measure distance in the rational numbers as follows. So I'm going to define a couple of things. So let me do this example here. So we're going to define we're going to find the norm and let me point out that first take A over B and write it as P to the N1 A prime, P to the N2 B prime, where now the first thing I've done in this first part of the construction is I've just basically jerked out every factor of P that I can find in A. Maybe that's 0 factors, right? And I've jerked out every factor of P that I can find in B below. And maybe that's 0 as well. But each Ni is greater than or equal to 0. N1, N2 are integers greater than or equal to 0, right? So I can write A over B as P to the N, A prime over B prime, where N is an integer. Basically, this N here is what you get with N1 minus N2. And that could be a positive integer, it could be a negative integer, it could be 0. And GCD PA prime equals 1 equals GCD PB prime. Everybody okay so far? And you sort of see why, perhaps you see why I threw 0 out of this consideration, because 0 has sort of infinitely many factors of P in it, right? And we'll deal with 0 later. We define the norm of this P to the N, A prime, B prime, the p-adic norm. I'm going to define it be P to the negative N. Now, this is kind of weird, because what this means is, and we'll define the norm of 0 to be 0. Notice that what this means, if you think about norms like from complex analysis or something like that, first of all, the bigger N is, the closer you are to 0. So for example, the element P is 1 over P. That's its distance, if you will. P squared is 1 over P squared, and so forth and so on. Notice that the unit circle, if you will, in this, is everything for which N is 0. So the unit circle just consists of all fractions that can be, basically it's all the units in Z localized at P, right? Because really what it means to be the unit circle is that N equals 0, and so you have A prime over B prime, which is just a unit in ZP. So the units in ZP are well, they're just sort of the unit circle in a certain sense. And we can define the distance between here, alpha, beta have no factor of P. numerator or denominator. Or synonymously, alpha and beta are in the units of z localized at p. I'm tired of writing fractions, so I'm just going to be lazy and do this. This is going to be right. Now, and the way you can do this is, so what happens with this? Well, if you look at the distance between p to the n alpha, whoops, my bad. Now notice that when is this zero? Well, it's zero if and only if I get a zero inside the bars here, right? Because otherwise, if this is anything else, then you get basically a power of p to the negative n. So we'll assume without loss of generality here, for computational purposes, that n is less than or equal to m. Correct? And so this is equal to p to the n times alpha minus p to the m minus n beta. Now let me point out a couple of things about this. Notice that this is p to the minus n if n is strictly less than m, right? Because if m is strictly less than n, then that thing is positive. And it's a simple computation to show that when you put, in this case, alpha minus p to the m minus n beta is still a unit in z localized at p. Because basically, if you put the fraction back together, the denominator still must be relatively prime to p. And now because you've got that power of p and a positive power of p, then the numerator is also relatively prime to p, right? So actually what happens is, in this case, get this. Now, what happens if n equals m, which is the only case? Well, then it's a crapshoot, right? Because what happens in this case is this could be, well, actually, I'll do this separately here. If it still might be p to the minus n, right? Unless the numerator of alpha minus, well, now it's going to be p to the 0, so I can write it this way. Alpha minus beta picks up extra factors of p in numerator. right? That could certainly happen, right? Because when you regroup alpha minus beta together, you might get extra. You're still going to have a denominator that's relatively prime to p, because when you multiply denominators, they just multiply. You can't pick up a p that way because it's prime, but you might pick it up in the numerator. But in that case, then what you have is you have p to the minus k with k greater than or equal to n. So in other words, this is smaller. Everybody okay with that? So we have the triangle inequality, right? Because the distance between Pn alpha and Pm beta is less than or equal to max length of Pn alpha. Right? Because if n is less than or equal to m, this is the piece that gives you the largest length, because the bigger exponent gives you a smaller output. So this one's the longer one, or maybe it's a tie, but it's at least the longer one, right? And so your output was p to the minus n or smaller. So this is actually less than or equal to the length of the two, the maximum length of the two sides, which is certainly stronger than the usual triangle. I mean, not only is it less than or equal to sum, it's less than or equal to the max. There is a weird p-adic geometry going here, because, for example, here's a couple of interesting consequences. This is a strong triangle inequality. Here's some weird consequences. In this notion of distance, for example, one, every interior point of a circle is its center. Every interior point is the center, which is weird. Two, all triangles are isosceles. So there's a weird notion of kind of distance. In fact, the triangle inequality is so strong here that all triangles are isosceles. And it's really weird because, for example, we're used to the notion of distance. Here's the origin. We're used to the real line, and say here's one, and let's say we're in the two-adic thing. Well, 2 is actually closer to the origin than 1, and 4 is closer to the origin than 0. However, at 1/2, you're further away. And at 1/4, you're even further than that. And 1/2n, you're very far away. But when you're used to thinking of the real line, between points that you're used to on the real line, it's sort of like a minefield in some abandoned war-torn country, right? Because you have these arbitrarily high powers of 2 that blast you very far away. It's very hard to kind of, reconcile this with, our usual geometric thinking of the real line. There's a couple of interesting sort of consequences there.
Do you know what the completion of the p-adic integers looks like?
Well, here we go. These aren't the p-adic integers yet, but so what you can do is, this is a field, or I'm sorry, this is a ring, right? But you can, let me see here. Where are you? There we go. For any prime p bigger than 0, we can introduce this notion of distance. And in fact, that's sort of a number theoretic result that we could discuss later if you want to come talk to me about it. But if you look at notions of absolute value on the rationals, it's a very famous theorem that up to equivalence, the only notions are the standard way to measure distance on the rationals that you're used to from the reals, just subtracting, and there's that notion of absolute value, and the p-adic absolute values for every p, right? But just like if you take the standard notion of distance on the rational numbers, you can complete it, right? You've all done this in like an advanced calculus class or an analysis class or something like that, where you look at Cauchy sequences and all this kind of business. And so from the with ordinary absolute value, we complete from Q to get R. Defining Cauchy sequences by, sequences that are getting closer and closer together. There's lots of different ways to do this. With the p-adic absolute value, we complete Q to get QP, okay? And this is called the p-adic rationals. And is quotient field. Of ZP, the p-adic integers. What are the p-adic integers then? Well, the p-adic integers, this is a Noetherian valuation domain. And is complete. I'm not going to talk so much about this at this juncture anyway, but this is another good example of a Noetherian valuation domain. So the p-adic integer ZP, and this is why in this class, in a beginning graduate or a beginning undergraduate class, and maybe even A8510, I might use this to be Z mod PZ. That's not a good notation here. This means the p-adic integers. This is a PID with a unique maximal ideal generated by P again. This one is uncountable. It's very, very large. Its quotient field is QP, and it's rather amazingly, it's Noetherian. Sometimes this is called a DVR, discrete valuation ring. I don't like to use that because there's some confusion. People in number theory, or people that do a lot of Noetherian stuff, would think that they equate DVR with Noetherian valuation domain, but Noetherian valuation domain is more descriptive, because often a DVR means it's a finite number of copies of Z lexicographically as the group of divisibility or the value group, right? So in my terminology, DVRs don't necessarily have to be Noetherian. Let me give you another construction So how could you get ZP? Well, you can do this business right here, just like you did in an analysis class to get QP, right? And QP is just the complete field that you get by taking the p-adic distances, equivalence classes of Cauchy sequences, et cetera, et cetera. Once you've constructed that, then take the p-adic value of evaluation on that field and apply this theorem 412. Just look at everything that's got value greater than or equal to 0, and you will get ZP, right? Let me give you something that I've actually used. It's a sort of a, well, I kind of like it because I've done a lot of computations with it, actually. Here's another way to think about the p-adics. How many of you are taking Sean's class? I think he's teaching class. What is Sean's class? I forget the title of it, but I thought it might be relevant.
Oh, it's homological ring properties?
Right. Has he talked about inverse limits?
He hasn't really talked about it, but we kind of covered briefly some stuff related to it, I guess. But
right. Well, I'm not going to really. I'm going to do a piss poor job probably. I'm not really going to cover it. But this construction is called an inverse limit, and I'll show you. It's dual to direct limit, which is direct limit is sort of a generalization of directed union in a certain sense. Let me show you another construction that's really kind of cool. This is an inverse limit construction. And the inverse comes from the direction the maps are pointing. And hopefully I'll clarify that later. Fix P prime. And like I said, I'm going to make this really kind of, my hands are getting dirty kind of construction. Consider Z mod P, Z mod P squared. Oh, I'm already being bad instructor here. Let me do it this way. Z mod P Z, otherwise it's a little circular, isn't it? Z mod P squared Z, Z mod P cubed Z, Z mod P to the n minus 1 E. Okay, so consider this sequence of very kind of, I hope, sort of intuitive rings. These are all, so the one on the left is just the field Z mod P. And the next one is Z mod PZ, or P squared Z, and then Z mod P cubed. Notice that, let's call this, I'm going to call these maps something here. Oops. Okay, and I hope you guys get the gist of this. The way I get from Z mod P squared to Z mod P is just take any element in Z mod P and then reduce it further mod P, right? So for example, 1 bar in Z mod P goes to 1, but so does 1 plus P, and 1 plus 2P, and 1 plus 3P, and so forth. And the same thing up here, from Z mod P cubed to Z mod P squared, 1 goes to 1, but 1 plus p squared, which is different than 1 in z mod p cubed, goes to 1 in z mod p squared, right? So pi pk is reduction mod pk. Now, I'm going to make this ring, and I'm going to consider, is this going to be enough? Yeah. Here's another construction of the p-adic integers. You can think of this as the set of all sequences, A1, A2, A3, AN minus 1, AN, forever, such that AI is in Z mod PIZ, and AI is equivalent to AI plus 1 mod PI. I do that right? Right. So, for example, let me do something. Let me do something concrete here. So let me write down Z3. Let's do kind of the 3 adics, if you will. So, for example, forever and ever, AI and Z mod 3IZ, and AI equal to AI plus 1 mod 3I. Okay. Let me give you some examples, hopefully, that might clarify some stuff that's in here. Just for giggles, let me start with a 1 here. So that's in Z3. Now notice, I can't have a 2 here, right? Because 2 is not equivalent to 1 mod 3, right? It's impossible. I've got to have an element here from Z9 that's equivalent to 1. So what are my choices? What could I put here?
You could put 1 or 4 or 7.
Right, I could put any of those. In fact, let me do something. I'm really glad you brought that up, Michael, because let me do something stupid. That works, right? And in fact, you can embed the integers into here. I notice that by just going in forever, right? Yes, up to a certain point, these n's might be reduced to something else, mod p, but once n is less than the power of 3, then it's all n's from there on out, right? So in other words, you can embed z into Z3, which you should be able to. But also you have things like you could have 1, 7, and now you move up to say mod 27, and it's got to be equivalent mod 9, so you could add 9 to that, and you could add 18 to that, or no, I'm sorry, you gotta go up a little bit. And now the 16-bit has got to be equivalent. What are we up to? 81. It's got to be equivalent mod 27, so I could add 54 to that. 54, that's going to be 70. And in fact, if you start here at 1, you can go 1, 4, 7, right? That is, you can add 0, 3, or 6, right? And if you have 4 here, you can go 4, 13, or 22, right? Because now it's got to be equivalent mod 9 here, right? And if you have 22 here, you can go up 27, or I'm sorry, you can go up 0. So you can go to 22, 22 plus 27, which is 49, and 49 plus 27, which is 76, and so forth. At every step, you've got 3 choices. Everybody agree with that? And so, in a certain sense, you can also sort of write in a sloppy way, A0 plus C1, 3 plus C2, 3 squared plus there we go, C3, 3 cubed, etc. Where each A0 is in Z mod 3Z, and each CI is equal to 0, 1, or 2. That sort of immediately shows that this Z3 is uncountable, right? Because, for example, you can think of, whether you think of it in this way or think of it in this way, you can think of an element as sequences of 0s, 1s, and 2s. Sequences of 0, 1, or 2, where you have complete freedom, where the 0, 1, and 2 determines how much you jump at every step, right? And so if you remember from real analysis, that's going to form an uncountable set. It's like a decimal expansion. Everybody okay with that? Here's something that's rather surprising. Notice that Z3 is a subring of the direct product of, so in fact, Z3 is contained in Z mod 3Z cross Z mod 9Z, Z mod 27Z cross forever, right? This is one nasty ring right here. It's got an identity, but it is very, very far from being an integral domain. There's lots of 0 divisors, right? So for example, in this ring here, Z3 cross Z9 cross Z27, I can have, let's say 1, 3, 3, 3, 3, and I can multiply, yeah, so let's go 1, 3, 3, 3, 3, 3 forever. I can multiply that by 0, 3, 9, 27, blah, 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 forever and ever, and I get 0. However, this is an integral domain. And in fact, it better be, since it's defined, since I first came up with it from its quotient field. So this restriction right here throws out 0 divisors, right? Even though it's uncountable, it throws out 0 divisors. Also, it's a principal ideal domain, which is not clear either, I don't think, at this juncture, but the principal ideal is generated by, in this case, 3, which is, well, it's 3, 3, 3, 3, 3 forever, which if you put it in terms of mods, it's 0, 3, 3, 3, 3, 3 forever. So this is a principal ideal domain, and this is another construction, and it's actually, this construction is good for figuring out things with units, because, for example, you can show that you have a unit in Z3 if and only if the first coordinate is a unit in Z mod 3. Well, Z mod 3 is a field, so anything that starts with a 1 or a 2 is a unit, right? If it starts with 0, it's a non-unit. And it's not a zero divisor unless it's all zeros. Okay, any questions on that? So there is.
Are there other integral domains between Z, the integers, and that very large ring that you had below?
You mean any integral domains between this and Z3?
Between Z and Z mod 3Z cross Z mod 9Z cross Z mod 27Z.
Oh, this one? Oh, yeah. Here's a professional terminology for you. There's a buttload of them. There is a lot. Yeah. And in fact, there are many rings between. So, yeah, I'm kind of glad you asked that question. So if you look at Z is contained in Z localized at 3, which is contained in p-adix. There's lots of intermediate rings in there, and let me give you a good example. Let me contrast this. In Z5, it actually turns out, so let me give you an example here. In Z5, this is, let me give you an element of Z5 here.
1, 1, 1, 1, 1, 1, 1.
No, I want something a little more sophisticated than that. 2, and let's see, what are my choices after that? I can add any multiple of 5 to it, and now I'm in Z25. Let's look at, I think I probably want
2, 7.
Actually, I think I want 12. Actually, let's see. Oh, actually, you're reading my mind there. Yeah, I want 7. And then do I want 32? I think I might want 32. 32 squared is 1024. Yep. And actually, I haven't proved this, but you can keep going. If you square this squares to 4, 49, 1024, blah, blah, blah. And let me rewrite this. Mod 5, this is -1. Mod 25, this is -1. Mod 125, this is -1, etc. So in Z5, there exists x such that x squared equals -1. So from one point of view, you can consider Z5 to contain an isomorphic copy of the Gaussian integers. Z3 does not have this property because the problem is there isn't even, if you look in Z3, there's nothing that squares to -1 because -1 in Z3 is 2. And if you square any elements of Z3, so you can't even make it -1 in the first digit, right? However, in Z5, you've got something that looks like I. So as an intermediate ring between Z and Z and the 3-adic integers, you can adjoin this strange element here, and it's essentially adjoining I. Right. This is one of the reasons the p-adics are useful in number theory, because they oftentimes they contain other algebraic. They're uncountable rings, but they often contain roots of other algebraic equations, and you can actually use the p-adics to determine if certain Diophantine equations are solvable and things of this nature. That's kind of where they come from. Okay, any other questions? Okay, so I can probably just begin to sort of define this here. So now that we've talked about valuations a little bit, talk about invertible ideals. Actually, one might think of invertible ideals. By the way, let me ask y'all something. Actually, how many of y'all, actually, I'm gonna stop sharing here so I can see all of you. How many of y'all have seen module theory? Have you seen Adam? Have you seen modules? Did you?
Yeah,
I might be misplacing the word in my head, but wait, modules.
you took the algebra with us last semester, right? We covered a lot of modules.
It's a vector space for rings.
Yeah, that's the one. Okay,
Yeah.
okay, good.
I just misplaced the word. Yes.
I was just curious how many of you had 8520 or something like that, where you had that. Okay, well, I might ask a couple of module questions to catch up on this, but actually, just like you might think of the concept of invertible as a generalization of principal ideals. Invertible ideals may not be principal. It turns out all principal ideals are invertible. Invertible ideals may not be principal, but they're very close. In a certain sense, and this is really a very good analogy because it's equivalent in many cases, invertible ideals are to principal ideals sort of what projective modules are to free modules, right? Projective modules are almost free in a certain sense. They're very close to being free. Invertible ideals are very close to being principal, although, well, from one sense, in one sense of the word. Let me give you a definition here before we go on our merry way here. Let R be a domain with quotient field K and R submodule I in K. So this is just an R submodule, right? I may not be closed under multiplication, but it's closed under scalar multiplication from R, is called, I got to tell you what this is first, a fractional ideal. If there exists a non-zero A and R such that AI is contained in R. Okay, so what's this all about? What does it mean to be a fractional ideal? A fractional ideal is just something like an ideal. It's an R submodule, so it's a subgroup of K. So that means that I consists of a bunch of fractions, doesn't it? Right? I mean, that are closed under addition. And the fractional part is a finiteness condition because what it says is there's a magic non-zero A that blasts I back into R. What that means is you can find a common denominator for everything in I. I consists of a number of fractions, right? And there is a magic denominator A that you can use for all the fractions. So that is everything in I can be written in the form R over a fixed A. This is a fairly strong finite condition on such a submodule. And this is the first step we need toward moving toward invertible ideals. And we will talk about this next time. Any questions before we roll out of here? Well, let me plug the math club again. I highly encourage you guys to come. It should be kind of an interesting talk. I kind of dig these kind of talks. But anyway, if there aren't any questions, I'll be around this afternoon if you need anything. And other than that, I hope to see you in the math club. Y'all have a good weekend.
Thank you, Professor.
You're welcome.
Have a
See you
good
later.
day.
You too.
Bye.